Hello everyone, this is Sandeep Singh. Welcome back once again in your favorite channel. I hope you are doing very well, and today we will going to discuss physics viral paper. That means it's a set of questions which are most predictable in your examinations, right? So just let me know audio and video is proper. Let me know in the chat box, and if everything is going good, then let's start the session for the second PU physics viral paper. All right. Hi Sivansh. Hello Shamuel. Hello everyone. Okay, fine. I think everything is going good. Hi Faz. Hello. Okay. That's great. Okay, fine. Before we start the session, let me tell you, PDF notes for the session is available in the description box with a link, right? You can click and you may download. Hi Sajanya. Hello Joshi. Hi Ambika. Hello Ramya. Hello everyone. Right. Now, let's start the session, and firstly, we will going to discuss one marker question, right? Right? These are very simple MCQ based questions. Let's start and try to solve. You also try to solve it, right? You can write your correct answer in chat box. All right, let's begin. Just put a thumbs up in chat box, then after we'll start the session. Let's put up thumbs up, then after we'll start it. All right, that's great. Hi, fine. Let's begin from very first question, right? This is what is the value of proportionality constant K in Coulomb's law in SI unit, right? Okay, fine. Let's see. What is the value of proportionality constant K? That is, see, F is equals to K Q1 Q2 upon R square. We will going to discuss about this K. Cross multiply this K Q1 Q2, which is equals to FR square, which means K is basically FR square upon Q1 Q2. And the value is 8.85 into 10 to the power 12 Newton meter square per Coulomb square. Newton meter square per Coulomb square. Is it? Okay. Okay, fine. Sorry. What it is? 1 upon 4 pi epsilon naught Q1 Q2 upon R square. And what is the value? This is 9 into 10 raised to the power 9, right? Newton meter square per Coulomb square. Right. And this is basically epsilon naught, 8.85 into 10 to the power minus 12. This is epsilon naught basically. And this one. Now, moving to next. What is an equipotential surface? Okay. What is an equipotential surface? Equipotential surface, that means a surface where the value of potential difference is 0. That means the value of potential at each point is same, right? An equipotential surface is a surface which constant value of potential at all points on the surface. That means potential difference is 0, and also work done in this surface in moving a charge from one point to another is also 0. All right. Moving to next. Define the term current density J. Basically, this is a vector quantity, and current density, that means what? It's a current, electric current upon area of cross section. Right? This is J is equals to I upon A. You know, I is a scalar quantity, but area is a vector quantity, so that J is a vector quantity. Alright? J is a vector quantity. Right? And what is the unit of this? current ampere per square meter, ampere per square meter. All right. Current density is a vector quantity often known as the area vector of cross-sectional area vector, whose value is equal to the electric current flowing per unit area, J equals to I upon A. Now, moving to next. Obviously, beta, this is a viral paper. Basically, this is a set of paper. This is a kind of sample paper. So, we are going to discuss in the same pattern as the questions asked in your second PU examination. Alright? Fine. A proton and an alpha particle enter the region of uniform magnetic field at right angles of the direction of the field with the same velocity. Which particle describes the greater circular path? You know, which having greater circular path. Basically, radius is directly proportional to the mass of the particle, right? Radius is directly proportional. Basically, radius depends on the mass of the particle. And which having greater mass? A proton having or alpha particle? As you know, alpha particle is heavier than proton. So, proton having less radius as compared to alpha particle. So that we can say greater circular path having alpha particle. Alright, let's see. Radius Rp equals to mp v upon Eb. Mp, that means mass. Mp, which means mass of proton. Mass of proton. And what is the v? V is the velocity. As in question, v will be the same for alpha particle and proton. And what about E? E is basically one electronic charge. That is 1.6 into 10 to the power minus 19 coulomb. Right? And this is B. B is a magnetic field intensity. Magnetic field intensity. Right? What it is? Rp equals to mpv upon Eb. And this is R alpha. Radius of alpha particle. This is 4 times of mass of proton. Right? Mass of alpha particle, which is equals to 4 times of mass of proton. So, R alpha equals to 2 times of R. R alpha is 2 times of R. Right? Mass 4 times, and electronic charge, if you are talking about electronic charge, this is just double than the proton. Right. Moving to next. Write the relation containing the angle of depth and horizontal vertical components of magnetic field of Earth at depth. Right? Samuel, just try to solve more number of questions. That's the only solution for this. Right? See, rank is directly proportional to number of questions practiced. Simple rule. Right? Right? Now, come to this question. This is basically the relation containing the angle of depth theta and the horizontal component BH and the vertical component VV, Earth's magnetic field at the place tan theta equals to VV plus BH. See, just like this, just consider this. See, this is basically BH, and in this way you have B vertical component and this is B horizontal component. If I am talking about this theta, then this is tan theta equals to BB upon BH. BB, that means vertical component, and this is horizontal component. Theta is the angle of dip or angle of inclination. BH is the horizontal component of the Earth's magnetic field, and BB is the vertical component of the Earth's magnetic field. Now, moving to next. Draw impedance diagram for series LCR circuit. This is the series LCR circuit, and what they ask impedance diagram, right? They ask impedance diagram, that means VI characteristics, right? See, as you know, for resistance, current is always at a x-axis. This is basically VR and this is VC. VC, that means potential due to capacitor, and this is basically VL. How to resolve these vector components? See, firstly we calculate VL and VC, then the resultant is VL minus VC. Is it? This is the resultant of VL minus VC with 90 degree of VR. Now, the resultant of these two, the resultant of VL minus VC and VR is this one. And what is the value of this? This is basically V is equals to under root of VL minus VC square plus VR square. Is it or not? Is it or not? Is it or not? Okay, fine. Sir, Kannada. Okay, but I am comfortable with English only. So if anything, if any point you have any doubt, then you may ask, right? Okay, that's great. Fine. Now come to the point. What it is? See, firstly, I'm just calculating. This is VC and this is VL. All right, having the angle of 180 degree. Two vectors are opposite in direction, then the resultant direction is what? Then the resultant direction is this one, that is VL minus VC. And as we know that there is no phase difference in potential and current and resistance, that means this is VR. So the resultant is this one. Okay? Okay, Sidhu? Okay, it's fine. This is the final fix. Alright? Now, moving to next. Give the frequency range of IR rays, infrared rays. Frequencies of infrared rays. What is the frequency of infrared ray? 8 into 10 to the power 10 to 4 into 10 to the power 14 hertz. These are the range. This is the range of infrared. Right? Right. Okay. Now, moving to next. An object is kept at a distance of 10 centimeter from a lens whose magnification is 1.5. At what distance from the lens image is formed? Okay, this is a very simple question, right? An object is kept at a distance of U is basically 10 centimeter. Right? Magnification is 1.5 and asking for V. And what is the condition? This is lens basically. This is lens basically. Just because lens having V upon U. Otherwise, in mirror, M equals to negative of V upon U. Alright, that's good. Now, putting sign convention, U will be always negative. An object is the distance 10 centimeter from a lens whose magnification is 1.5. At what distance from the lens image is formed? Now, simply, M, that is 1.5. This is positive basically. So, negative of U, that means V equals to negative of 50. V equals to negative of 15. Is it? Is it? This is in centimeters, so that the final answer is in centimeters. Okay, fine. Fine. 15 centimeter. Is it? Now, moving to next. What do you think? Moving to next. Okay, it's fine. Let's moving to next question. Write the expression for the de Broglie wavelength of an electron accelerated through a potential difference of V volt. Just write down the expression for the de Broglie wavelength. It's a direct question. Sir, explain derivations. Yeah, obviously, Sidhu. Obviously, in 3-marker question and 5-marker question, we have lot of derivations. Right? We have lot of derivation. Fine. Now, this is lambda equals to h upon p. H is a Planck's constant. H is a Planck's constant, and P is a momentum. P is a momentum, right? According to de Broglie wavelength, an electron, after being accelerated by the potential difference of V volts from rest, is lambda equals to h upon P, which is lambda equals to h upon P, momentum. P is basically under root of 2 MeV. Alright, that's why lambda equals to, just put the value of h, Planck's constant, 12.26 upon under root of V. Is it? Now moving to next. Okay, what is the wave number of a spectral line related to its wavelength? What is the wave number of a spectral line related to its wavelength? See, this is V dash is equals to 1 upon lambda. V dash is basically wave number and lambda is wavelength. This is the simple relation, V dash equals to 1 upon lambda. Okay. Now, moving to next. What is forbidden energy gap? This is the energy gap between conduction band and valency band in semiconductors, right? This is the energy gap between conduction band and valency band in semiconductors, due to which no electron hole pairs recombinations occurred, right? But after a certain potential difference, it will be happen, and it seems to be like a conductor. Okay. The energy gap between the valency band and conduction band is called forbidden energy gap, right? Now, moving to next, mention one advantage of frequency modulation over amplitude modulation, right? Frequency modulation over amplitude modulation. What is the advantage? See, as you know, here is less noise as compared to AM. FM having less noise as compared to AM, but there is some disadvantages also, right? AM transmitted at longer distance, but FM can't. So, as per question, improve signal to noise. I hope everything is going good. I hope everything is going good right now. So, right. Okay, it's fine. Moving to next question. Sorry for the interruption. Now moving to next question. Let's see. Okay, it's fine. Let's solve the 2 marker questions, right? Let's solve the 2 marker questions. Write an expression for intensity of electric field in vector form and explain the terms, right? What it is? Electric field intensity in vector form, that is E, which is equals to KQ upon R square, now converted into in vector form, that is E vector is equals to KQ upon, this is KQ upon R square having R cap. This is R cap. You can also written as this is E vector, which is equals to KQ, right? R vector upon modulus of R vector cube. As you know that R cap, which means R vector upon modulus of R vector. Is it? R vector upon modulus of R vector. Okay. Now, moving to next. Factors which capacitance of capacitor depends. Just try to solve factors which capacitance of capacitor depends. I'll be right back. I will be right back. Just wait. I'll be right back. So, okay, it's fine. Okay, it's fine. Okay, it's fine. Right. Yeah. Yeah. Factors capacitance, distance, area, and epsilon naught. Right? Epsilon naught represents permittivity. Right? Medium between two plates. Medium between two plates. Medium between two plates. Right? Area of each plate, distance between the plates, and the dielectric constants of the medium between the plates. That is nature of the medium between two plates. All right? All right. All right. Now, moving to next, define the terms drift velocity and relaxation time. Drift velocity and relaxation time. See, drift velocity is just like it's a average velocity of one free electron. All right. Whereas this is relaxation time. This is a time lapse between two successive collisions. It's same like you are in your assembly hall before prayer, and what is going on, right? You're just starting gossip with some student, then after another student, then after another student. That is what is relaxation time. Relaxation time is just like you just talk with one of your friend, and then after you move towards another friend, then the time lapse between talking first friend, then after second friend is called relaxation time. Same like this. This is the time lapse between two successive collisions. All right. Okay. What did I see? Drift velocity. When a potential difference applied across a conductor, the free electrons drift towards the direction of positive potential. The small average velocity of free electron along the direction of positive potential is called drift velocity. Represented by this is Vd. Right? Vd. Okay. Same like relaxation time. The time of free travel of free electrons between two successive collision of electron with the lattice ion or atom is called relaxation time. Represented by this tau. Right? Okay. Moving to next. Represents the direction of magnetic field into the plane of the paper and emerging out of the plane of the paper. What else? This is the magnetic field. Everyone knows this is very simple question. What is into the plane of paper? Into the plane of the paper. Into, that means what? Into, that means cross. Into, that means cross. And for the second one, emerging out. Emerging out. That means it seems to be like a dot. It's dot, 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 dot. These dots shows the magnetic field lines outward the plane of paper. Right? This is the outward from the plane of paper. So, see, this is outside, this is inside. Now, moving to next. When is the torque acting on a magnetic needle or by a magnetic dipole in a uniform magnetic field maximum and minimum? See, tau, which is equals to mb sin theta, right? Tau is mb sin theta. Just because tau is equals to m vector cross b vector, is it? In magnetic field. This is in magnetic field, right? This is in magnetic field. Similarly, in electrical field, it is pe sin theta. All right. Then, as you know, for tau max, there will be maximum value of sin theta. And where is the maximum value of sin theta? At 90 degree. Tau max at theta equals to 90 degree. That is tau max, which is equals to mb only. Just because sin 90, which is equals to 1. Whereas tau mean, see, at 0 degree, and if I'm talking about negative of 180 degree, that is minus of m. 0 degree, where theta equals to 0 degree, right? Sin 0 is 0. That means tau min is 0. For another case, we have tau at 180 degree. What it is? Sine 180, negative of 1. Is it or no? Not. Let's see. They ask only two conditions. We have to write these two. See. Torque at maximum at 90 degree, tau minimum at theta equals to 0 degree. Okay. Let's moving to next. Magnetic flux linked with the coil is changed from 1 Weber to 0.1 Weber in 0.1 second. The induced EMF, right? Induced EMF E is equals to negative of basically d phi upon dt, which may be written as negative of, this is del phi upon del t also. All right. That means negative of phi 2 minus phi 1, phi 2 minus phi 1 upon del t. From 1 Weber to 0.1 Weber. That is 0.1 minus 1 upon 0.1. Is it? Is it or not? Okay, it's fine. Okay, it's fine. Minus 0.1 minus 1 upon 0.1, 0.9 upon 0.1, that is 9 volt. It's okay? Okay, it's fine. State Ampere's Maxwell law, write the mathematical form. Ampere's Maxwell law, write its mathematical form. See, this is also called modified Ampere circuital law, right? This is modified Ampere circuital law after containing the Maxwell's equation, that is introducing displacement current, conventional current plus displacement current. All right. See, this is basically before Maxwell's current, B dot dl is equals to mu naught times of I. This is mu naught times of I. But when introduce Maxwell's current, that is displacement current, then this is mu naught times of IC, which is conventional current, plus mu naught times of epsilon naught times of d phi E upon dt. Epsilon naught times of d phi E upon dt. This is the modified version of Ampere circuital law. This is basically displacement current. What it is? This is basically displacement current. Displacement current. Or you can say this is also known as Maxwell current. This is Maxwell current. This is Maxwell current. Is it? Obviously, Samuel, what is the result of your first attempt? What is the result of your first attempt? Okay. Mention the conditions for destructive interference in terms of path difference and the phase difference of interfering waves. See, this is mention the condition for destructive interference. As you know, if two waves are opposite in direction, this is destructive waveform. Then the resultant will be amplitude this minus this, then the resultant will be just like this. All right, this is destructive wave. Conditions. See, destructive interference occurs when two waves cancel each other out, or resulting a minimum or zero intensity. This happens when the crest of one wave overlaps with those of another wave. That is condition for the path difference. What is the condition of path difference? See, del x equals to 2n plus 1 lambda upon 2. Odd numbers. This is basically odd numbers. You can put 0, 1, 2, 3, but always you get odd multiple of lambda upon 2. This is the first condition. This is the first condition, and condition second for the phase difference. This is for the path difference. This is phase difference. Phase difference is basically phi equals to this is also odd multiple of pi. Odd multiple of pi, that means 2n plus 1 into pi. Where n is 1, 2, 3, 4, 5, 6, n integer. All right. All right. Okay. Don't worry, Samuel. you just try in your second attempt, right? You can solve rank accelerator. That will help you in your second attempt, right? Fine. Okay. Now, state and explains radioactive decay law. Radioactive decay law. See, what is radioactive decay law? The number of nuclei undergoing the decay per unit time is proportional to the number of unchanged nuclei present at that instant. That means what? This is negative of dn upon dt is directly proportional to n. And if you remove or you can eliminate this proportionality sign, you will get lambda as a constant. Lambda is known as the decay constant or disintegration constant. The negative sign indicates the disintegrations of atoms, right? This is basically decay law. This is basically decay law. Okay, let's moving to next. What it is? Draw the graph showing the VI characteristics of PN junction diode in forward bias and reverse bias. PN junction diode, it's very simple. See, in forward bias, here potential and this is the value of current. Somewhere this is basically VC, cutoff voltage, right? And in reverse bias, seen like this. This is in reverse bias, this is in forward bias. Again, this is current and this is potential. What we see here, see, this is basically VP. This is the breakdown voltage. And what about this? This is due to leakage current or current due to minority charge carrier. As you know, semiconductor is not a ohmic device, not a ohmic conductor, so that there is no linear change in resistance with respect to potential. Alright? Sidhu sir, derivation explain. Which derivation, Sidhu? Which derivation? Okay, this is in forward bias, this is in reverse bias. Mention any two communication system which make us of space wave method of propagation. Space wave method of propagation, right? Why MCQ? Why? Why are you worried? Asperia. Okay. Why you are worried? See, television broadcast and satellite communication all use the high frequency space wave, hence these use space wave method of propagation, right? Now, let's come to the 3-marker question. These are the direct questions, right? Specific question, but from 3-marker questions, you see like derivation type questions and you have numericals also. So, let's start 3-marker question. Just put a thumbs up in chat box, then after we will start. I hope there is no issue with 1 marker and 2 marker. Alright. And Sidhu, is there any specific derivation you have or you have any specific doubt? Then let me know. Aspira, for this, you just try to solve MCQ series, right? 50 and 50 questions per day. Try 2 or 3 sessions for this. You have get confidence, right? You get confidence, yeah. Okay, let's begin. 3-marker question. Derive the expression for the torque experienced by an electric dipole placed in a uniform electric field. See, Sidhu, see. What is the value of this? This is tau is equals to P sine theta. This is tau equals to P sine theta, right? P is dipole moment. This is dipole moment. And what about E? electric field intensity. And what about theta? It's an angle between P vector and E vector. So that we can written as tau vector, which is equals to P cross E. Is it? Let's derive. See. Just consider uniform electric field. This is basically uniform electric field. Is it? This is basically uniform electric field. And I have a dipole. This is a dipole. This is Q negative basically, and this is Q positive. Alright? Q negative having the direction of force QE this way, and positive of QE with the direction of electric field. Positive of QE with the direction of electric field. Now, if I'm just considering this dipole is named as AB, this dipole is named as AB, then just construct this portion and put C. Right? Okay, let's see. What is this QE? Basically, F is equals to QE. Force acting on each charge. See, if an electric field like this way, and I'm just putting a dipole, so here positive charge, then the force acting on this positive charge in the direction of electric field, and the force acting on negative charge opposite to the direction of electric field, so that let's start rotating, and that force is called basically torque. Torque is basically momentum of force. All right. So see what it is. Torque, which is equals to force into perpendicular distance. Force into perpendicular distance. And force is what? This is QE. This is QE. Okay. So this is QE. And what about perpendicular distance? This AC is the perpendicular distance. Kept it AC. Now, see, since from the diagram, what we see in diagram, see, sine theta is equals to AC upon AB. And AB is what? This is the length of dipole, and length of dipole is how much? It's 2L. So, AC is equals to AB sine theta, which means this is 2L sine theta. This is 2L sine theta. So, tau is equals to QE into 2L sine theta. Now, as you know very well, this Q into 2L, since this 2QL, which is equals to P, dipole moment, electric dipole moment P. So, can I return as this tau as this like PE sine theta? So that we can return as this is P vector cross E vector. This is the complete derivation of torque acting on an electric dipole in uniform electric field. Alright? Alright? This is easier. This is an easier one. Okay. You have a standard answer also. You have a standard answer also. So don't worry about that. And the session PDF link given in the description box. Alright? After the session, you may download it. Obtain the expression for the relation between electric field and the electric potential. Electric field and electric potential. You know electric field and electric potential. It's called potential gradient also. See, as you know, E is equals to KQ upon R square. And what about V? This is basically KQ upon R. Then what is the relation between these two? It means V is equals to E upon V equals to E equals to C KQ upon R into 1 upon R. Then can I written as KQ upon R? KQ upon R is a V, that is V upon R. But with the negative sign. If we are moving with the direction of electric field, there will be loss of potential, and against the electric field, rise in potential. Same like this. See, I'm just talking about gravitational potential. On this marker, gravitational potential acting towards gravitational field acting towards to the center of the earth. Now, if I'm considering the direction of this pen moving upward, this is against to the gravitational field, then rise in potential, and along the gravitational field, loss in potential. If I'm moving down, there will be a loss in potential. Similarly, so we can written as E is equals to dV upon dr with negative sign. E equals to negative of dV upon dr. This is potential gradient. This is rate of change. This is rate of change, and rate of change is also known as potential, also known as gradient. E equals to negative of dV upon dx. All right. Okay. Arrive the expression for the electric current in terms of drift velocity. Electric current I equals to NEA VD. Let's we have calculate. I equals to NEA VD. N is the number of charge cases. E is the one electronic charge. A is the area of cross section. And what about the VD? VD is the drift velocity, and this I is a current. Okay. See. The average velocity of free electrons in conductor is called drift velocity of electrons in the conductor when the conductor is connected to a source EMF of electric field established E equals to V upon L, which is generally known as E equals to V upon R. Here R is this like L. L is the length, right? V is the potential difference. L is the length of the conductor. Now, A equals to negative of E upon M. This is nothing but, this is C. F equals to M, as you know very well. F is what? This is QE. So that A equals to what is? EE. Q is just one electronic charge, and this is electric field upon M, but with negative. All right. See, and what about the VD, drift velocity? Drift velocity, that is EE upon M into tau, right? This is the VD. See, acceleration. What is the acceleration? Acceleration, you know, this is velocity upon time. Then what is the velocity? That is acceleration into time. Is it? Is it? Similarly, this is basically acceleration. Can I multiply with time? Time, that is relaxation time. Time, that is relaxation time. So that what is VD here? VD is basically A into tau. A is what? This is E upon M into tau. Got my point? And what is E here? This is V upon L. Negative of V upon L. Just put it all. You have to reach at point I equals to which is Q upon T. Now, Q is what? Q is basically NALE upon L times of VD. L just cancel out. I is equals to NAVD. NAVD. Just E also. This cancel out. E also. Just remember, I is equals to Vena. VDEN. Right? Just remember, I equals to Vena. I equals to Vena. VDEN. Right? I equals to Vena. It's a short form to learn. Right? Okay. State and explain Biot-Savart's law. Just straightforward question, explain Biot-Savart's law. Biot-Savart's law is basically used for the magnetic field intensity at a point due to a current carrying conductor. Alright, if you have a current carrying conductor, just like, see, this is the current carrying conductor of I ampere, and you have a point, this is a point P. This is a point P. I have This is integral length dl. This is integral length dl. Then the magnetic field intensity at point P due to this current carrying conductor, as Oersted told, that is magnetic field present around the current carrying conductor. Now we have to calculate the intensity of that magnetic field intensity. Then let's join this. This is basically the angle theta. This is basically r vector. This is point P. And using curl rule, as we know that the magnetic field intensity in the direction of inside, so that let's put cross at this point P. Magnetic field inside, right? So, as Biot told you, that is dB, magnetic field intensity due to this integral length dl, magnetic field intensity due to an integral length of dl, integral length of dl at any point with r distance apart, with r distance at angle of theta. Then dB is directly proportional to current. dB is directly proportional to this integral length dl. dB is directly proportional to sin theta, and dB is inversely proportional to this square of distance, which means combination of these, all these relations, we have dB is proportional to I dl sin theta upon r square. If we remove this proportionality constant, we remove this proportionality sign, we have a constant which is mu naught upon 4 pi. Alright, I dl sin theta upon r square. Or you can written as dB is equal to mu naught upon 4 pi is basically 10 to the power minus 7. 10 to the power minus 7 I dl sin theta upon r square. Basically, this expression comes, see, in the same way. See, this is the I ampere of current, this is the dl, right? And the magnetic field intensity at this point P. See, dB is it's a vector quantity. That is 10 to the power minus 7 I dl sin theta upon r square. See, this is a vector quantity. But as you know, this is a scalar quantity. This is a scalar quantity. But smartly current consider a direction vector. How is it possible? Current as a director form? Current in a vector form? How is it possible? Smartly use current. This is called current. Basically, I'm not a vector quantity, but I'm considering a direction vector. How is it possible? Say this is dl vector. So current is basically I dl vector. This is not alone I, this is basically I dl vector. So that it behaves like a vector quantity, right? This is current is very smart, right? So if I'm considering here vector, this is also r cap, which means dB vector is equals to 10 to the power minus 7 I. dl vector cross r vector upon r cube. You got my point? Current itself is a scalar. Current itself is a scalar. But as you know, we want here sin theta. That means it comes from cross product. How can I put cross product, that is I vector cross dl vector? Is it possible? No. So we put a direction vector, that is r cap, which is equals to r cap basically r vector upon modulus of r vector. That's it. You got the basic agenda, right? This is basically bias. Okay. Directly proportional to the current, directly proportional to the length of the current element. This is dB is directly proportional to I, dB is directly proportional to current element, that is dl. and the directly proportional to the sine angle of that is dB is directly proportional to sine theta, and inversely proportional, that means dB is inversely proportional to r square. On combining these all, dB is equals to 10 to the power minus 7 ideal sine theta upon r square. Okay, anyone having any doubt? Then let me know. Okay, now define self-inductance of a coil. Define self-inductance of a coil. Derive expression for the magnetic energy stored in the inductance cell. Right? This is basically half Li square. All right? This is basically half Li square. Energy stored half Li square. In capacitor, that is half CV square. Right? Okay. Let's see. Self-inductance of a coil defined as the ratio of the total flux linked with the coil to the current flowing through it. This is the flux linked with the same coil, right? L equals to N d phi upon dt. N d phi upon dt. N is what? Number of turns. Phi is magnetic flux link. I is the current. All right. What about the electric field intense? What about the EMF induced across that coil? See, as you know, what is self-inductance? See. This is a coil. If I ampere of current passing through it, due to this I ampere current, there will be a magnetic field. There will be a magnetic field across this coil. And this current is basically AC. See, this is an AC current. So that it's varying. It's varying. And due to change in magnetic field lines into the same coil, there will be induced EMF. And what that is? Negative of L d phi upon dt. L d phi upon dt. L is basically coefficient of self-inductance. L is basically coefficient of self-inductance. Okay? Right. EMF equals to minus of N d phi upon dt, that is negative of L di. Right? L di, sorry. Di. L di upon dt. The self-inductance of EMF is also called the back EMF, as opposes any changes in current in the circuit. So, work needs to be done against the back EMF in establishing the current. This work done is stored in magnetic potential energy, that is dW upon dt. Magnetic potential energy dW upon dt, which is EI. E, that is basically magnitude of EMF, just because EMF having negative sign, and this negative sign shows that it opposes their cause of change. All right, so that L di upon dt. Now integrate both sides. W equals to dW, that is L di upon dt. That means half of Li square. Right? See, half of Li square. Okay. Explain clearly how Maxwell was lead to predict the existence of electromagnetic wave. Right? Existence of electromagnetic wave. See, on the basis of Faraday's law, electromagnetic induction and modified Ampere's Maxwell law basically, theoretically predict that the existence of electromagnetic wave, the field changing with time gives rise to electric field, that is integration, close integration of E dot dl, which is equals to d phi upon dt. E dot dl equals to d phi upon dt. And what is the upgraded version of the Ampere's Maxwell rule? Right? That is B dot dl equals to mu naught IC plus mu naught epsilon naught d phi E upon dt. This is, you know, this is the conventional current and this is Maxwell current. This is a displacement current basically. It means laws of electricity and magnetism are symmetrical. The consequence of this symmetry is the existence of electromagnetic wave. According to the Maxwell, an accelerating charge produces electromagnetic waves, and electric charge oscillating harmonically with frequency V produces an electromagnetic waves of the same frequency nu. Right? Same frequency nu. All right. Done? Done? Okay. Which are the common defects in human eye? How to rectify them? Common defect, as you know, 3 common defects, that is myopia, hypermetropia and presbyopia. Myopia, hypermetropia and presbyopia. Alright? Myopia, nearsightedness, corrected by concave. Hypermetropia, farsightedness, corrected by convex. And presbyopia, corrected by bifocal lens. You know, bifocal lens is just like this, right? As you see, some uncles wearing this specs, right? I know everyone knows about this. This is for nearby objects. This is for near objects. And for near objects, what do you use? You use convex lens. This is convex lens. And this is for far objects. And this is concave lens. Right? This is concave lens. Yeah, Simon, that's great. Now, can we move another question? Can we move to another question? Okay. Let's see. Define threshold frequency, walk function and stopping potential. Threshold frequency. Threshold frequency. This is a frequency before that no photoelectric emission happened. Right? Before the threshold frequency, no photoelectrons emitted from the metallic surface or photo surface. All right. After the threshold frequency, they ejected from the metallic surface and the electric circuit completed, then you have got the electric current. But before that, no. That's why this is called threshold frequency. Right? This is threshold frequency. This concept given by Einstein, right? Okay. Now, next, what about the work function? Work function is the energy required to just skip the charges or electrons from the metallic surface. This is the energy required to just escape the charges from metallic surface. Then after, you know, you have your energy basically expresses in 2 ways. First thing is in work function and second one is in kinetic energy. What it is? Work function, that means you have to just escape that electron, and remaining energy moving to in its kinetic energy. See, it's same like one of your friend is in hostel, right? And you have sitting with the guard uncle, right? You have sitting with the guard uncle, and let's just localite over there. You have 1,000 rupees, right? You have 1,000 rupees, and you just set it the guard uncle worth 300, right? So you just put 300 to guard uncle to move your friend from hostel, right? And remaining 700 rupees to party, right? Same way. See, this is the total energy. This is basically work function to just escape from hostel, to just escape from the metallic surface, and remaining the energy portion, that is 700, is to party. That means to give kinetic energy of the electron. Is it? Is it? Right. Okay. And what about the stopping potential? Stopping potential, it's same like someone wants to stop you, but you can't. See, stopping potential is just like, see, as you know, the apparatus of this photoelectric emission, see, this is the quartz window, this is completely vacuum, and this is photosensitive plate. This is a quartz material. Now, if a beam of light falls on this plate, there is an ejection of electron and moving towards here. This is basically anode and this is basically cathode. You have to complete this electrical circuit. Just put here a potential difference is negative and this is positive. Due to this positive, this electron gets attracted by the anode and circuit completed. You have photocurrent. But if I'm considering this cathode will be positive and this anode will be negative, reverse the potentials. This is positive and this is negative. Then the potential, if anode turns into negative, so that not even a maximum kinetic energy of electron moves from cathode to anode, then that potential is called stopping potential. That potential is called stopping potential. Anode at negative potential, cathode at positive potential. How much this potential required? That much potential, due to which not even maximum kinetic energy of electron can reach the anode. Right. Okay. See, the minimum frequency of incident light for a metal surface below which the incident light cannot eject electron is called threshold or cutoff frequency for that metallic surface. Work function, the minimum amount of energy required to eject an electron from the surface without imparting any kinetic energy is called work function. And what is stopping potential? The value of negative potential of the collector corresponding which even the fastest photoelectrons, right, are repelled back is called stopping potential. It is also defined as the minimum value of opposing potential difference required as to just stop the photoelectrons emitting with the maximum kinetic energy. It is also called cut-off potential. Stopping potential is also called cut-off potential. Okay? Okay, fine. Now, obtain Bohr's quantization condition for angular momentum of electron obtaining an nth hydrogen atom on the basis of the wave picture of an electron using de Broglie hypothesis. See, according to de Broglie, lambda equals to h upon mu. ठीक है, h upon में lambda equals to h upon p. P equals to basically mv. mv is momentum, mass into velocity. Right. Now, the nth orbit, right, wavelength of the nth orbit is 2 pi r and lambda. Right. Now, since angular momentum L equals to mvr, this is the angular momentum, this is momentum, right. L equals to hr upon lambda. That means hr upon, what is the value of lambda? That is 2 pi r upon n. Lambda equals to 2 pi r upon n. 2 pi r upon n. All right. Explain why modulation is necessary in communication. Explain why modulation is necessary in communication. As you know, in a communication system, Mason's signal having not enough power to arrive at receiver end, so that modulation required. All right, we modulate Mason's signal with a high frequency carrier signal, and then after we target that power to reach at receiver end. The modulation process, some parameter of carrier wave such as amplitude, frequency and phase, that is amplitude modulation, frequency modulation and phase modulation, right, is varied in accordance with the modulating signal. This modulating signal is the transmitted by transmitter. It is necessary to modulate the signal because first, it avoids mixing of signals. If the baseband sound signals are transmitted without using modulation by more than one transmitter, then all the signals will be same frequency range, that is 0 to 20 kilohertz. Therefore, all the signals get mixed together and A receiver cannot separate them from each other. See, my frequency is same like 0 to 20 kilohertz. Some other one wants to communicate, then they have also the same frequency. Then both are mixed together. So that we need a carrier wave that is possible due to modulation. All right. Okay. It increases the range of communication. The frequency of baseband signal is low, and the low frequency signal cannot travel long distance with when they are transmitted. They get heavily attenuated. The attenuation reduces with increase in the frequency of the transmitter signal, and they travel longer distance. If I just say something and without carrier signal, it can't transmit it at a longer distance, right? See, so that average power over a complete cycle in pure inductor connected to an AC source is 0, right? See, so that average power of a complete pure inductor, see, this is pure inductor. As you know, power, average power, P average, which is equals to IRMS into VRMS into cos phi, is it? And what is the phi? Is basically phase angle. This is basically phase angle. This is basically phase angle. And in inductor, you know very well. In inductor, you know very well. This is I. This is VL. And the phase angle is at 90 degree. See, I equals to see, VL equals to V naught sine omega t. Right? Potential is leading by 90 degree. That means I naught sine omega t minus pi by 2. This is the equation for current in inductor. Potential is leading, right? And potential having the same equation, V equals to V naught sine omega t. So this leads by 90 degree. That means current is just behind 90 degree. That's why I'm just putting omega naught minus pi by 2. All right. Now, on comparison, we have phase angle of 90 degree. And as you know, since phi is equals to 90 degree and cos 90 is how much? 0. That means P average is equals to 0. No power loss in inductive circuit, purely inductive circuit. In purely capacitive circuit also there will be no power loss. In LC circuit also there will be no power loss. Power loss only happen in resistive circuit. If I have LCR, then in inductor and capacitor there will be no power loss. Only power loss occur in a resistive circuit, right? That is across resistance. Now moving to next, that is 5-marker question. Moving to 5-marker question. I hope till this question you have no any doubt. If it is, then just let me know in the chat box. If there is any doubt, then just let me know in the chat box. Okay? Okay. Let's moving to 5-marker question. These are basically essay type question. Essay type question does not mean you have to write some essay. This is basically a longer question. That means you have to derive some expressions. You have to explain some diagrams, just like workings of transformer, working of full wave and half wave rectifier. Right? These are basically essay type question. And for 5-marker question, you have to cover answer in 5 points also, right? In 5 points also. In which question? Just like you have to describe transformer. Then just putting what is transformer. I'm just explaining a general question, right? What is transformer? This is the first point, right? What is transformer? What is transformer? This is the first point. Second, working principle. Working principle, right? Third point is the basically working. Fourth point is a diagram. You have to put a diagram. And the what about fifth point? This is basically losses in transformer. Losses in transformer. Alright. There will be numerical, there will be theoretical and derivations also. So let's start. See, using Gauss law, derive the expression for the electric field due to an infinite long straight uniformly charged wire. This is very simple question. This is very simple question. See, I'm just considering this is a current carrying conductor. Let's see, this is a charge conductor. Okay, sorry, this is a charge conductor. Just draw a Gaussian surface. Just draw a Gaussian surface. Gaussian surface, basically it's a symmetrical surface which cover this charge conductor. How is it possible? This is possible in this way, cylindrical and uniformly charged wire, infinitely long. See, this wire is basically infinitely long, infinite. Firstly, we have to calculate finitely long, then just put the value, right? The value of theta is 90 and 90, then you get the infinitely long wire, right? Yeah, this is the first application of Gauss theorem. Yeah. Okay. Okay. Just see. This is lambda, basically Q upon L. L is the length of the conductor. L is the length of the conductor. This is L is the length of the conductor. Q is the charge per unit. Q is the charge and lambda is the charge per unit length. Lambda is the charge per unit length. Right? Okay. Okay. Now see. As you know that integration of d phi e, or you can just like see integration of d phi e close, that is equals to E dot ds, right? E vector dot ds vector. Let's remove this integral sign. E dot ds, E vector dot ds vector. D phi e is basically E ds cos theta. Now theta is just 0. That means d phi, which is equals to E ds. All right. Now close integration taking both sides. D phi e is basically phi e, phi suffix e, that is electric flux. What about this? E into integration of ds. And what is the lateral surface area of the cylinder? That is E into 2 pi RL. This is 2 pi RL. R is what? This is radius basically. A is 2 pi R. This is equation number first. This is equation number first. Now from Gauss law or Gauss theorem, what it is? It is phi e is equals to Q naught times of charge, right? 1 upon epsilon naught times of Q naught. That is basically Gauss law. 1 upon epsilon naught times of total charge present inside the vessel. That is 1 upon epsilon naught times of this. That means phi e is equals to, as you know, see, lambda is a linear charge distribution, right? That is Q upon L. Then what about Q? That is lambda times of L. Just put it lambda L upon epsilon. This is lambda L upon epsilon. This is equation number second. You have two equations. First equation is phi equals to E 2 pi RL, and you have second equation phi equals to lambda L upon epsilon naught. These two are same, right? This is also phi E. Now from equation first and second, what we have, this is E into 2 pi r L, which is equals to lambda L upon epsilon naught. This L cancel out. Then E is equals to 1 upon 2 pi epsilon naught, 1 upon 2 pi epsilon naught, lambda upon Newton per Coulomb. Newton per Coulomb. Right? Right? Okay, fine. Fine. Okay. Yeah, you can just draw. See what it is. See, if I'm just considering this is the first diagram ds1, right? This is ds vector. This is basically ds vector, and this is basically E vector. 90 degree, that means there is no flux. Now, if I'm considering this is ds2, in this way, this is ds2, and electric field intensity in same like, okay, electric field intensity is same like, this is also 90 degree, that means this is also 0. Phi basically here cos theta, cos 90 is 0. Let's see, this is ds3 basically, this is ds3, and electric field intensity also in the same direction. That's why I'm considering this theta equals to 0 degree, right? This theta equals to 0 degree on this basis. Okay? Now, it will be okay? Okay. 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 You got? Yeah, obviously it's required. Obviously it's required. Okay. Now, what is meant by equivalent resistance? Derive an expression for the equivalent resistance of two resistors connected in parallel. This is too easy question. Too easy question. As you are considering in PU second, this is too easy question. This question just like a question for class 10th, right? See, let's suppose this is R1, this is R2, this is R1, this is R2, and a potential difference V across this combination. Then we have I ampere of current. Now what we see as per diagram, as you know that potential difference in parallel combination are same, only the current divides. See, in this way I1 and this is I2. From here this will be I. That means I, which is equals to I1 plus I2, from Ohm's law, it's V equals to IR, which means I equals to V upon R. Is it? I1 equals to V upon R1, and I2 which is equals to V upon R2. Just because, as you know, potential is constant. V is constant in parallel combination, right? So what it is, I is just basically V upon R, which is equals to V upon R1 plus V upon R2. V common and cancel out, that means 1 upon R equivalent, which is equals to 1 upon R1 plus 1 upon R2. That means R equivalent, which is equals to R1 R2 upon R1 plus R2. I think you got. This year's exams feels very tough. Sir, I haven't seen such type of question in the paper before. So don't worry. This is a sample paper basically. This is the sample paper, so don't worry. It doesn't mean that each and every question is tough and toughest. So, right? It doesn't mean, right? Okay. This is a sample paper, official, right? These questions already asked in your second PU examination, not framing by me, right? Yeah. Okay. Now moving to next. Obtain the relation between magnetic susceptibility, magnetic permeability of substance with permeability of free space. right? See, in always in PU examination, moderated questions asked, all right? Not only in PU, if you are talking about 12th board examination also, right? In 10th board examination also, there will be a moderated question paper, all right? Then, uh, then you have a doubt how variation of marks arises. Variation of marks arises on the basis of your representation. How to present, how to answer these questions in 3 hours. That's matter. All right. All right. One or two questions that decides the toppers. Otherwise, 20 to 30% questions are easy, right? 20 to 30% questions are easy. About 30 to 40% questions are moderated. 20% questions just like it's tough, or you can say like moderated plus, right? Only 5 to 10% questions are tough, and that not mean tough. That basically the questions that decide the toppers, that differentiate the toppers and average student. All right, all right. Lisa, Lisa, where is the problem? Just because we derive each expression, and we already cover numericals too, right? If anyone having any specific doubt, then let me know, right? Okay, else we discuss each and every question in descriptive way, right? Okay, see, the total magnetic field inside a material is the sum of magnetic field due to external source and the magnetic field due to the magnetization of the material is M. Mathematically, this is B equals to mu naught H plus M. B equals to mu naught times, see, B equals to mu naught times of M. This is basically M plus H. This is magnetization of material, and this is due to outsource. Susceptibility, XH, right? From the definition of magnetic susceptibility, M equals to XH, substitute M into the equation of B. This substituting by XH. Now the form is B equals to mu naught times of H plus XH, that is mu naught plus 1 plus, alright? This is basically magnetic susceptibility. This is magnetic permeability, and this is magnetic permeability of free space. Now, from the definition of magnetic permeability, B equals to mu naught times of H, right? That is mu H equals to mu naught H plus 1 plus, right? So, can H both side? Let's cancel out this. Mu equals to mu naught times of 1 plus X. Now, the final relation, the relationship between magnetic susceptibility, magnetic permeability mu, and the permeability of the free space mu naught is mu equals to mu naught times of 1 plus X. Mu equals to mu naught 1 plus X. Is it? Okay. Now, moving to next. Derive the expression for the width of interference fringes in Young's double slit experiment. Fringe width in Young's double slit experiment. Right? Expression for the fringe width. Fringe width, how to calculate fringe width? Just put N1 and just put N2, right? Just we have to calculate Xn and Xn plus 1. Now the fringe width, that is X del X, is basically Xn plus 1 minus of Xn. Nth fringe, and considering N plus 1th fringe. That means we have to calculate a fringe width, that is, I just consider third and this is as fourth. Then what is the fringe width? This is just like, see, this is first fringe, second, third and fourth. What is the fringe width? This is the fringe width, right? How to calculate? Calculate fourth fringe minus third. Fourth fringe minus third. All right? Right? Okay. Okay. See, as we know, del x is equals to n lambda. Del x equals to n lambda for bright fringe. This is for bright fringe. And del x is equals to n plus 1. Okay, n plus 1 upon 2. Sorry, n plus 1 lambda upon 2. This is for dark fringe. This is for dark fringe. All right. See. D is the separation between the slit and the screen, and D is the spectral distance between this. D is much greater than D. D is much greater than D. Then, under the above approximation, let's see. See. I just draw. This is a single source, right? Right? This is basically D. Okay. Now we have a screen. This is a screen. A light beam moving from here. This is a source 1 and this is source 2. These are monochromatic lights, synchronous monochromatic light basically. Now from here to arrive this point P, this beam of light moving this way and this is in this light. Now the distance between this screen and the slit is D. Now see, you have to just put it, see, this is just basically origin. This is D upon 2 and this is also D upon 2. Now, this complete distance is just suppose like X. Alright? That means, what is the distance from, see, this point considered as AB. What is AP? What is AP? This is basically X minus D by 2. This is basically X minus D upon 2. And this is basically from BP, this is X plus D upon 2. X plus D upon 2. Is it? Now I think everything is clear. See, as you know, for brighter fringe, this is del X equals to D Y upon D n lambda. Right? This is for brighter fringe. That means Y equals to n D upon, see, let me write, del X is equals to D upon D, right? D upon D is equals to n lambda. Then what about this? Y. This is n lambda D upon D. N lambda D upon D. Now just put Y equals to 0 plus minus of D lambda upon D. First thing, n equals to 0, this one. N equals to 1, D lambda upon D. N equals to 2, 2D lambda upon D, 3D lambda upon D, and so. Alright. Now, Y equals to plus minus D lambda upon 2D, Y equals to plus minus 3D lambda upon 2D, Y equals to plus minus of 5D lambda upon D, and so. Now, the width fringe therefore is D lambda upon D. D lambda upon D. Right? Right? Okay. Okay. Now, give Einstein's explanation for photoelectric effect experimental observation. Einstein explanation for the photoelectric effect. Einstein just put the concept of threshold frequency, work function, right? That means the total energy is expenses into two way, that is in the form of work function phi naught or omega naught, somewhere omega naught also, right? Or you can h nu naught also. This is work function basically, plus kinetic energy maximum kinetic. Total energy expenses into two parts. This is energy which is equals to work function plus maximum kinetic energy. plus maximum kinetic. Therefore, we can write kinetic energy maximum, which is equals to h nu minus h nu naught, or Ke max, maximum kinetic energy. H is it's a Planck's constant. Nu minus nu naught. Nu minus nu naught. All right. Nu minus nu naught. Total energy minus work function is basically your kinetic energy. Your pocket money, that was 1,000 rupees, minus your pocket money, 1,000 rupees, minus the amount spent on guard uncle, that is 300, then the remaining 700 for your party. Is it? Okay. Okay. Right. See, when ray of light is incident on a metal surface, then it absorbs this energy and emits the electron from the surface of the metal. Sometime electron is not ejected because incident energy is less than the work function of the metal. Right? The maximum kinetic energy of emerging electrons is independent of intensity of incident radiation, but depends linearly on the frequency of the radiation. See, you don't have sufficient frequency, but you have lot of intensity, but there will be no electronic emission possible. Electronic emission possible after the threshold frequency only. All right? Intensity will not ejected the electrons, and one photon is eject one electron. One photon is eject one electron. See, if you have, as previous example, see, we discussed somewhere, right? We discussed somewhere. Yeah, this one. Sorry. Yeah, this one. See, you have 1,000 rupees. You have sitting with the guard uncle at hostel of your friend. You have 1,000 rupees. You don't spend your amount in just like, see, uncle, I have 1,000 rupees. Can you leave 3 persons? Just because you have sufficient amount, that is 900 rupees you have. But guard uncle told, no, it's not possible. One student asked for only one student from hostel. All right. That means in similar like one photon can eject one electron only. Irrespective of you have lot of energy. That doesn't matter. All right. Okay. Okay. Now, electrons start emitting immediately after the light shine on the surface without detectable time lag. No any time lapse. Why it is possible? How is it possible? There is no time lapse. Just because this is an elastic collision. Emitting of electron and striking of photon, this is a single event. This is not just like some energy comes absorbed by the electron and reaching some value and then after ejected. No, it's not possible. After threshold frequency, striking a photon and emitting of electron, this is a single event. So that no time lapse, right? For given frequency of incident radiation above V0, the number of electrons emitted per unit time is proportional to the intensity of radiation. Higher intensity having higher kinetic energy. But for ejection of electron, there will be a certain frequency that is called threshold frequency, right? What is rectifier? Describe the construction and the working of full wave rectifier, drawing input and output wave. What is rectifier basically? Rectifier is basically which converts AC signal to DC. We have to convert AC signal to DC. And there will be two types of rectifier. First one is the half wave rectifier. Half wave rectifier. Half wave rectifier. And second one is full wave rectifier. See, basic difference between these two: half wave rectifier having 50% of capacity, this one having approximately is 100%, but it's not true. As you know, 100% never possible. Nearby of 100%, nearby of 100%, this is nearby of 50%. Alright. See, this is just because here using one diode, only one diode. Here using two diodes. How it works? See, it's very simple. This is a symbolic representation of transformer. I'm using two diodes and a central trap transformer. Alright, this is a central trap transformer. Okay, this is diode D1, this is diode D2. This end named as A, B, this named as CD. Alright, here V in, right, and here V out. Okay, or VL called. Okay. To draw this diagram, is there any problem? Is there anyone having problem with the diagram? This is the diagram of basically full wave rectifier. This is the diagram of full wave rectifier. Is it? This is the full wave rectifier. Now see, AC source at the input end. See, just focus on the color combination, you will get the working. See, if at this input end, this signals come. See. Yeah. You can just draw. This is the input signal. This is input signal. And I have to draw output signal here. Just skipping the same phase, I have to draw these dotted lines. These are nothing, these are just showing the phase, right? See, this is the output and this is input. Okay, now see. As you see, if positive half comes at the input Vi, if positive end comes at the input end, just keep in mind the color combination. A is at higher potential, B is at lower potential, just because this having the higher potential and this is at lower potential. As you know, this is at higher potential, this is lower potential. This is also at higher and this is lower potential for that. All right, but in negative direction. Now see clearly. This is at positive, this is at negative. That means C is at positive and D is at negative. If C is at positive, that means this is at positive end and N-type semiconductor is connected at negative. That means this is in forward bias, circuit completed through this, current moving just like this. And this D2, see, this is at negative potential and this is at positive. That means it does not conduct. That means it's open circuit, just like this. This is an open circuit. Just because this is negative and this is positive. That means it's in reverse bias. So see, working. See, in short way, how to learn the working. In short way, how to learn the working. I'm just writing. See, for this, as you know, A and B. A is at higher potential. A is at higher potential HP. B is at lower potential, accordance with C and D also. C is at higher potential, D is at lower potential. So that D1 is in forward bias and D2 is in a reverse bias, which means they conduct and this is open. Is it? Is it? Then what it is? Current circuit completed through this way. That's why I'm using central trap transform. So you have output potential just like this due to D. Now I'm using yellow for the negative phase. This comes here. So that B is at positive. This is higher potential and this is lower potential. Now this is at lower potential. C is at lower potential and D is at higher potential. Now this time, this is at lower and this is at higher potential. And this is at higher and this is at lower potential. That means D2 is in forward bias and circuit completed this way. Right? Circuit completed this way. But the direction of current through this load resistance is the same, just like the first one. Right? This name is same. That means what? If negative phase come at this point, what it is? A is at lower potential, B is at higher potential, accordance with C and D also. Just because this is a transformer. Now, D1 is in reverse bias and D2 is in now forward bias, so that this is open and this conduct. But the important thing is the direction of current will be same. That means I have output in the positive phase. Same like this one. Now, next positive phase come at input end and D1 now D1 conducts so that output this output due to D2. Now what you will see, this AC, which means alternating, the direction changes rapidly, now converted into pulsating DC. We don't have any negative phase. We have DC, but it's pulsating DC. Increasing the value of DC, then decreasing 0. Right? 0 to max, 0 to max, 0 to max, 0 to max. But here, 0 to positive max, now 0, then negative max, then 0, then positive max, then 0, then negative max, then 0. That's why it's called AC. And this is DC. This is basically pulsating DC. Alright? Alright? Lisa, see, if you are considering the purple one, that means this one. If you are considering the purple one, that means this one. This one. A is at higher potential, B is at lower potential. B is at lower potential, that means this is at lower potential. If P-type semiconductor connected at negative potential, that means it's a reverse bias. In reverse bias, PN junction diode never conduct. Alright? Yeah. Session PDF is available with the link of description box. Alright? Just give me some time. After completing the session, it will upload it. Right? Yeah. You may check after 30 to 40 minutes. Right? There will be a link, but PDF uploaded once class is over. Lisa, is there any doubt? Is there any doubt? Polarity changing, sir. Yeah, obviously. This is basically AC. This is basically AC. What I am saying, just keep in mind the color combination. For this color combination, this is as positive, this is as positive, this is as positive, this is as negative. That means D1 conducts. This is at lower potential, that means this is at lower potential. P-type is at lower potential, this is higher potential, that means D2 in reverse. Now, the second half of AC, second half of AC, this one, second half of AC at input end. Second half of AC at input end, that means this is at higher potential and this is at lower potential. That means B is at higher potential, A is at lower potential. A, which means C is also at lower potential, D is at higher potential. Now, if the diode D2 connected P-type material with the higher potential and N-type at lower potential, that means this is in forward bias, whereas C is at lower potential, D is at higher potential, right? So, P-type material is connected with lower potential, that means it is in reverse bias. D1 is in reverse bias, that means it's open circuit. It's open circuit, just like this. For negative half, the circuit will be like this. This is open circuit. That's why using two diodes in half wave rectifier, only one diode. That means for the positive D1 conduct, for this positive it's conduct. For negative halves, there will be no conduction. Yeah. Obviously, Sheetal, we already done with numericals also. This is a viral question paper. This is a question paper same like your second PU question paper, right? Yeah. This is same like that. This paper is basically most viral paper, that means most predictable question in the format of your second PU. Alright? Yeah. You got the point? Now you have to elaborate each and everything, the diagram of the full wave rectifier, then the workings. I'm just putting in points format. You have to write in the paragraph format. Then after, this is the output. This is the output. See the question, what they ask. What is the rectifier? Describe the construction. Describe the construction. This is the construction, right? But you have to describe. I have a model answer 2, so don't worry. And then after, working of full wave rectifier, draw input and output waveforms. This is input and output waveforms. This is working. Now, this is the theory. This is the complete theory. Don't worry about that. See, I'm just putting the resistance here only. See, this is the central trap transformer. This will also draw in just like this. So don't worry about that. You can draw the simplified one also. You can draw this one also. This is the theory. This is the construction. This is the construction part. This is the construction part. This is the working part. Right? This is the working part. See? Right? I think if you understand the concept of this full wave rectifier, then you have to write in your own words. Alright? You have to write in your own words. All right. Now, these are the most important questions for your second PU, and basically, this is a kind of sample paper. This is a kind of your final examination paper, just because we designed this viral paper on the same pattern as your second PU. All right. So this time we completed the session. So just like the session, share the session, and subscribe the channel. All right. Just share with your friends. Right? Okay, fine. Now, you have any doubts? You have any particular doubt related to this paper or any other topic? Let me know in the chat box. Otherwise, we'll meet in another session, and then after we'll discuss some more important questions, some more important numericals, more important MCQs also, right? So we'll meet in next session. All right, kindly continue the series. Yeah, obviously, Lisa, obviously we continued the sessions, right? Already you have done with your biology viral paper, maths viral paper, and chemistry viral paper, right? Yeah, I think you're done with Okay, sir. Okay, fine. Let's end the session, and the session PDF notes you may download in with the link of the description box, right? So we'll meet in next session. Thank you so much. Bye bye. Take care, everyone.